was trying to tell you is that, so we have the modifications to Rankine cycle. So today I will cover the modifications to Rankine cycle and talk about each modification and draw TS diagram for each. So you can see there are 7 modifications, and each modification increases efficiency. At the beginning, we have started with 26%, and then it is 49.2%. Each modification increases efficiency, but the problem here is that each one has the advantage and the disadvantage. Okay, we should be very careful about these applications. Okay, now let's start from the first one, and I will draw the TS diagram for each of it. Okay, for the first one, the operational, so you have to give care about this, that pressure line. So you have the lowest isobaric line, so this is 75 kilopascal, and the highest isobaric line, which is 3 megapascal, and the peak temperature is 350 degrees Celsius. And if you remember the Rankine cycle was something like this one. You had the, draw it here, you have the boiler, and then you have the turbine, and then you have the condenser, and the pump. So boiler, you have the steam in the turbine, from the turbine to condenser, and from condenser to pump, and from pump to boiler. So this was the general configuration of the simple ideal Rankine cycle. Now let's draw the TS diagram for the first one. Okay, so that we have the 75 kilopascal and the 3 megapascal with a peak temperature of 350 degrees Celsius. So wait, firstly, so 75 kilopascal, and then you have that 3000 kilopascal, and the peak temperature is at 350 degrees Celsius. And this one is that you will have here pump, and then boiler, and then turbine, and then condenser. So these are the numbers that we are putting here. So the pump starts from 75 kilopascal, and that transfers water to 300 kilopascal, 3000 kilopascal, and the P4 is 75, you are here, and then 3000 will be P2 line, and then this will be 2, and this one will be 1. This is isentropic, and then you will have the boiler. This part is the boiler part. Boiler is at constant pressure. Okay, this is heat exchanger, and heat exchangers are at constant pressure, and it rises the temperature to 350 degrees. This one is the point 3. And boiler, condenser. Okay. These are heat exchangers, and heat exchangers are at constant pressure. Okay. So then from the 3 to 4, you will have the turbine, and it goes in an isentropic manner too. So turbine will be in that way. So you will have this process here. Okay, so you have the 4. This is the process direction that you are going to have. Okay, now next is that what you are doing is we are adding the modification number 1, which is that we are increasing the pressure. So sorry, we are decreasing the boiler, the condenser pressure here. It should be 10 kilopascal now. So let's write the first modification here. So that modification, that you will have that now 10 kilopascal and 3000 kilopascal, and the peak temperature is the same. Okay. Now let's do that. So you will have that the pump now works from this point, which is at 1 prime, to the same pressure line here now is 2 prime. Okay. But the boiler part will be that amount. This one will be the boiler. Okay. And then from that 3 to 4, everything is there. So you have that same values here, so it doesn't change, but only the boiler, the condenser pressure drops. So you will have that 4 prime here, and then the pressure of the condenser. Okay. This is the result of the modification. Okay, so as a result of this modification, you can see that we have talked about this one, that the turbine inlet has more moisture content turbine inlet has more moisture content. You can see it here. So at the turbine inlet, you have that this amount of the moisture content, so it is dangerous for the turbine, but efficiency has increased. And as you can notice from here that now the boiler also is doing more heat transfer, because in the previous case, it was increasing from this temperature to that 3, but now it starts from 2' to 3. Okay, you can see that the boiler energy input has also increased. If you look at the chart here, you can see at the beginning it was that 2,700, now it is 2,900. Okay. Okay, so this is the, and also the work of the turbine, that it has increased, because now you can see that turbine is doing this amount of energy transfer. So there is this amount of energy transfer in the turbine, therefore the efficiency of the, that work output of the turbine has increased. The work of the pump, it doesn't change too much, because that you can find the work of the pump by using that nu dp relationship. And since it is incompressible, nu will be constant and will be nu delta p. And for the water, that for this pressure change, nu is so small that it doesn't affect the overall result of the work of the pump. Okay, good. Now comes that modification number 3. What you are doing is that you are increasing the peak temperature to 600 degrees Celsius, but everything is the same. So let me do that. So I will add, now the peak temperature was at 3, now it becomes at 600 degrees Celsius. Now you will be here. Okay. So that this chart, so it will go to point 3', okay? And now the work of the turbine, you can see that it has also increased. So you will have that 4 double prime, and the rest will be the same. Okay, but the good side for this one is that you can see that now you have more quality. So that 4', so more quality than 4 double prime, actually has more quality than the 4'. So this is the modification number 3. You can see that I've increased the temperature here, so that efficiency has also increased, and the quality, you can see it increased. It is good for the turbine, because the water is dangerous for the turbine. It can erode the blades of the turbine, and these turbines are steam turbines, and therefore what you want is that only steam. Okay, so quality has increased, efficiency has increased. It is because that the temperature has increased. If you look at the chart, you can see that now the turbine works from that pressure to this pressure. Okay? So you can expect in the increase of the work of the turbine, you can see that they are getting more electricity. This one is electricity. So you are increasing the value of the electricity. But heat input also increased, because now what you are doing is that you are heating from 2' to 3'. So the boiler part has also increased. And the heat output also increased, because now in the previous case it was from 1 to 4', but now it is 1 to 4 double prime. So this is the condenser part. So you can see that after this modification, as a final result, the combination of this increase and the decrease is that you have increase in efficiency, which is in the amount of the 37.3%. So now comes the last, that efficiency, which is that we are now increasing the pressure here. So I can write what happens at each step. So in the second step, P condenser, so drops. So then you have that temperature peak increases, and now what we are doing is that P boiler, the boiler pressure increases. So instead of playing with the temperature value here, we are playing with the pressure, because that the increasing temperature, you have to need the material that can withstand that high amount of the temperature. But it is not the temperature alone that increases the energy of the working fluid. Pressure also is a type of energy. So that if you increase pressure also, it means that steam will have higher energy. Okay. Therefore, now let's do the last part. Now I will increase the pressure to 15 megapascal, but the temperature will be the same. So this one will be the last one. And now let me use different color here. So this one is also not good because it's not visible. So I will use color here. Okay, now it will be that 3 double prime. Okay, so now the pump will start from 1 prime to that part, the 2 double prime. So you can see it is the next modification. So here the pump starts from 10 kilopascal to 15 megapascal, and then comes that part of the boiler here. So this is the boiler part that you are going to have. Okay. So boiler increases the temperature to that amount. Now comes the work of the turbine. Now the work of the turbine will start from the 3 prime again back to the condenser pressure. Okay. So I don't know where it will coincide, but let me draw it. This is the last modification for this simple ideal one. But you will see that in the next parts, you will also add on the. Okay, so it will be that for triple prime. Okay, there is that one. So you will have that for triple prime. Okay, now that the cycle will be something like this one. Okay, so this is the last modification, and as a result of this modification, so you can see that the efficiency increased 43%, and then quality also dropped because at the beginning you were around here, but now you've gone to the left part. And moving to the left means that you have increased the moisture content. You have increased this moisture content, and this one means that it is liquid, and this one is not good for the turbine. It is dangerous. Okay. So therefore, we have to be very careful about this one. But you can see that the moisture content has increased. Therefore, you should play with these values, and you can move to the right, or you can add the components to decrease amount of the moisture content that you don't have any problem. And also that the pump work has increased, but you can see that now the pump starts from 10 kilopascal to 15 megapascal. Okay. This is the pump work, so from 10 kilopascal to 15 megapascal. So therefore, this one increased. You are doing more work. And then the heat input, so it is decreased. So heat input has decreased. And then, but you have that, so the work of the turbine has also increased because that you have, in the initial case, you have this amount of pressure. So that P2 was, you can see it was that 3 megapascal and 600 degrees Celsius. These are turbine inlet. Okay, so here inlet was 3 megapascal, and then you have that 600 degrees Celsius. Now the inlet is 15 megapascal and 600 degrees Celsius. You can see that you have more energy at the inlet of the turbine. So this more energy means that the turbine can do more work, and more work means that you have at the end it will affect the efficiency. Good. This is the another modification that we have added to this simple ideal part. And these 4 ones are only for that simple and ideal Rankine. Okay. So you're just adding different, so you're not adding, that you're playing with the values of the condenser and the boiler, and you are affecting the efficiency. But at the end, you should remember that these are only due to that eta is 1 minus TL by TH. Okay. And the TH is boiler, and the TL is condenser. You are playing with the condenser temperature, you have to drop it so that this comes, and you have to increase the boiler pressure, so boiler temperature. You increase this one, you drop that one, at the end efficiency gets closer to 1. Okay. And all of these modifications here are only for that purpose: decrease condenser temperature and increase boiler temperature. Okay. Good. So that is, this one is for the ideal one, but if you are looking for the real one, you have to get with QL divided by QH, and this QL is that the condenser one. I can write this one as condenser, and this one that boiler. You have to play with these values, and this one all proportional to these temperatures. Good. Now I'm going to the next modification where we are using two-stage turbines. We are going to use two turbines here. So a reheat cycle. This is also called that reheat cycle. Let's do that. So for reheating, so what will I have is that, again, I have the boiler here, and I have the pump here, and the turbine. One, I have the first turbine, but this turbine is also called that high pressure turbine, or HP turbine. And from that boiler, you have that inlet to the turbine 1, but this turbine outlet, so it is again sent back to this boiler here, and it is reheated. So here, reheating process. And then goes back to inlet of the next turbine here. So you are adding another turbine here. So this one is called that low pressure turbine. And these two are connected with shaft. So here you have that shaft here that connects these two turbines together. So it means that they are rotating at the same speed with the same shaft. So by doing this one, you are increasing the inlet temperature of the turbine 2. So this one is the reheating process. And then from this turbine 2, you will have again the condenser back. And from that condenser, you will get the pump. And from that pump, again, back to the boiler here. But you should keep in mind that this one is not mixed with the boiler. This is a different line here. And if I continue, for example, this one inside the boiler, you will have something like this one. Okay. This one goes in that direction, and this one goes in that direction. Okay, now let me put some numbers here and plot the TS diagram for this one too. Here I will have that number 1, and then that inlet of the boiler, you will have that number 2. You will have the turbine inlet, which is 3, and the outlet here, which is 4. And then inlet of the second one, which is 5, and here you have that 6, and then back to 1 again. So it is very similar to, so you are getting power in stage, and this one is similar to compressor by intercooling. So if you remember that we were compressing the fluid in 2 stages. We are compressing to some intermediate pressure, and then cool the fluid, and then compress it again. So it is 2-stage compression. But here, instead of using 2-stage compression, you are doing the opposite, 2-stage expansion. So at the previous case, it was 2-stage compression. Now you will have that 2-stage expansion. But it can be 3-stage, it can be 3-stage too. So then if it is 3-stage, you can have that high pressure turbine, then intermediate pressure turbine, and the low pressure turbine. 3 turbines at the same time. So let me see if there's a, let me see. For example, for this one, you can see this turbine here, it is that high pressure turbine. And this turbine here is that it is low pressure turbine. So let me use a different color here. It is low pressure turbine. And in between, you will have that reheating. Okay, so that this one is the inlet for this one, and you will have another pipe here that it diverts it back to the boiler here, and it is reheated and goes inlet to the second turbine here. Okay, and then the second turbine gets the power, okay, and then it is sent back to condensers. This is the condenser here. Okay, and this is the generator. So you can see that there are 2 stages, and the high pressure turbine and the low pressure turbine. Even if you can see the same shaft here, they are coupled, and they have a coupling here, and they are rotating with the same speed. Okay, and this is the condenser. I think we have talked about these ones, the components of this one, and this is the pump here. That you can see after the condenser, you have the pump stage and back to the boiler stage, and this is the boiler. But the boiler, and this one is very huge building. The turbines also. Let me see if there is a real picture for the turbine. You can see the real picture here for the turbine. Okay, this one is that low pressure part of the turbine, and this part is the high pressure part of the turbine. And this one is connected to this shaft, to some generator, and you get the electricity. The real turbine is huge. For example, in this Azerbaijan power plant, so we have talked, there are 8 units here. And it means that you will have that 8 turbines, and each turbine with intermediate stage and with high pressure stage and a low pressure stage. At the end, you get this amount of the power. Okay, good. Now let's draw the TS diagram for this one, but before drawing it, let me get the values from the table here. The values is that you are working with 10 kilopascal to 15 megapascal and with a peak temperature of 600 degrees. So you will have that 10 to 15 kilopascal and the peak temperature is 600 degrees. So this peak temperature happens here after the boiler. So this one is that you have peak temperature here, temperature peak. And here you also have the maximum amount of the pressure because it is after the boiler stage and also after the pump stage. Therefore, you will have the maximum amount of the temperature and the maximum amount of the pressure. Okay, now let's draw it on the TS diagram. So I will first start from point 1, and this point 1 is at 10 kilopascal. And then from point 1 to point 2, now it will be at 15,000 kilopascal. Then from 15,000 kilopascal, boiler is isobaric. The pressure will not change, and this one will be again 15,000 kilopascal. Then the turbine T4, that the pressure here, we don't know that pressure, P4, and it is unknown. So P4, let me say that some pressure P4. We don't know it. So if you solve the problem, so if you solve it, we will get that P4. I don't have time for that one, and that or P5. We can solve it. But you see that P4 goes to the turbine here, so the boiler, sorry, boiler. But it gets back. And here we don't consider the pipe losses, delta P losses in pipeline. So we don't consider that one, therefore that P5 should be the same as P4. We have the same pressure here. And then you have from the turbine 2, and here again the pressure drops, but you should keep in mind that P4, the pressure at 4, is less than pressure at 3, because here you have used the energy of the fluid. The energy of the fluid, if you have used it, its pressure should drop. Okay, it has lower enthalpy here. And then you have the P5, which is the inlet of the turbine 2, and then from that P5, from inlet of the turbine 2, the pressure again drops to P6. And since it is condenser, and this one is also isobaric, so that 6 should be the same as 1. They should have the same pressure because it is isobaric. Therefore, it is also 10 kilopascal. Okay. So this is the general chart here. And for any pump, so for these cycles, so the pumps we have here at inlet, so often you have that X is 0. The quality is 0. This is the minimum criteria, or it should be that compressed. The minimum criteria is that it should be 0 quality or compressed state. This compressed state is also called subcooled state. Okay. Now let's plot it on the TS diagram here. So I will start from the 10 kilopascal, which is point 1, with X is 0. But I've said it, you can start from here, or you can start from here, or you can start from here. It doesn't matter where you start, but you should be very careful that inlet of the pump should be liquid. If it is gas, then there is problem. For the sake of these problems, we are always starting with the ideal case where you have that minimum criteria, and minimum criteria is that here you have the liquid. Okay, then the pump pumps from 1 to 2. So it will go in isotropic manner to the last pressure line. So let me go there. Okay, and this is the point 2. So you have the point 1, and this is the point 2, and it is pump. And then from the pump, you have the boiler stage, and that boiler stage is from that to a peak temperature of 600 degrees Celsius. This is 3. So I got that 3 stage, so you can see it. 600 degrees Celsius and with the same pressure line, P1. So that the boiler is isobaric. The pressure should be constant. So I draw that line here. This should be isobaric because it is boiler. Okay, now that part. And then this one. Okay, and then from this point, this is the boiler pressure. Then comes that 4, which is the turbine stage, and the 5, which is turbine 2. But 4 and the 5, I've said it, we don't know the solution, and if you solve it, you will get this P4 and the P5. But if you go back to the chart here, you can see that one more property is given. This one is given, and this is the quality. So that, sorry, moisture content, and these two values and this one and that one are given. So if these two values are given, so it means that, and here I know the quality here, 6. So at this point, quality is given, and that quality is 0.896. So therefore, the condenser 6, and here you have the qualities. It should be very close to 1, but about the point here. Let me use the color back again. So the quality here is 0.896. And the point here is that this is the 0.6. And this is the condenser stage. Okay. So, and from, I will go backwards. From 6 to 5, you will have this turbine 2, which is isentropic. I will go backwards. I don't know where the 5 and the 4 will meet. I don't know it. Okay. And for this one, so let's assume, but we don't solve the problem. But if you solve the problem, you will get the P4 and the P5. So that P4 is 4 megapascal. We are assuming that P4 and the P5 is 4 megapascal. I said it, it is the same pressure. The pressure losses inside the pipeline are not considered. Therefore, you'll have that. So you can see that this one is P3, it is 1.2 megapascal, and the P2 is 3 megapascal, and I should go that P4 line. So that P4 should be approximately here. Okay. Approximately here. This is the 0.5. You can see that I have 5 to 6. This is the turbine 2. And now comes that turbine 1. It should go from 3 to 4. But before doing that, I should draw the 4 megapascal line. And the 4 megapascal line should be something like this one. This is the 4 megapascal pressure line. So 4 megapascal. This is the 4 megapascal pressure line here. Okay. And the 0.5 is there. You have the 0.5 here. Now, so you should go from that turbine 1, which is from 3 to 4. Okay, that turbine 1, 3 to 4. I should stop here. This is the 4, because that P4 is at 4 megapascal. So I should stop at 4 megapascal, but it should be isentropic. That direction and this direction. It's the direction of the, that is the direction of the cycle. Okay. Now that from 4 to 5, I have the reheating. So that 4 to 5, what is that? Reheating. And reheating is that you have that increase of T, the temperature increase, but as well as since it is Q in, you will have that entropy increase. So therefore, from 4 to 5, I will have that reheating stage, but this reheating is at constant pressure. So you can see it is at constant pressure. Therefore, I will go in that way along the constant pressure line. Okay. So the direction will be upwards. Okay, so this is the chart for the turbines with reheating. Okay, so if I go back to the efficiency part here, You can see that I have added two-stage turbines here. The efficiency has increased to 45%, and the work of the turbine has also increased, and the heat output increased. Okay, these are the values that you can get it by solving the problem. And okay, the reheating helps, this one, helps to get more power from the turbines. Very similar to compressor. You are doing the opposite here, because you are increasing this energy and getting back to turbine 2. But the problem here is that, so if you have lots of turbines here, at the end you can decrease the efficiency. So because that will not decrease the efficiency, you will have that constant amount of efficiency because you are using the heat of the boiler, okay, for this intermediate heating. You are not using additional source. This is the heat of the boiler. Okay, therefore, you should have some compensation for using that, because if you need more heat, that means that you have to use more fuel, and more fuel means that at the end again it affects the efficiency, and it can drop the efficiency. Good. So this is the one more part of the cycle. We're using reheating, and this reheating also, if you can notice it here, is that it increased the quality here. At the beginning, quality was here. Where is that? Here. This one was the last modification. But now the quality has increased to this point here. Beyond the, so it was, let me show it here. So 4 triple prime in modification. Let me see what was the modification number. It was 4. At 4, modification number 4. So modification number 4, you have that 4 triple prime here. But by using reheating, you can see that quality has increased. So you've moved towards the right part of the chart here. And by moving to the right part of the chart, you have increased the quality, and it is good for the turbine. Okay, now comes that next modification here. Okay. That next one will be using this open feed water and the closed feed water heaters. So that we have regeneration cycle with open feed water heater, and these are the values that are given for the open feed water heater. So what is that? Now let's see it. So this is the feed water heater. So okay, this feed water heater, you can see that there is a steam inlet from the turbine, and this is the feed water inlet here, and then you have this feed water outlet. You can see it. These are the pipelines, and this one is open feed water heater. You can see there's one outlet for the feed water, and this is the drain line for this one. Okay, now why do we use this one, and what is the open feed water heater? And let me show it with a simple component-wise manner. So I have the boiler here, and then I have the turbine. So I'm not using reheating, okay? There is no reheating. I have the turbine, and this turbine outlet goes to the condenser here, and this condenser outlet, so I don't do anything, just wait for that part. And here also, I have the pump, okay, and this pump also waits here. What you are doing for this open feed water heater? For open feed water heater, so this is the, let's say this one is the inlet. So you are extracting steam. Extracting steam, or it is also called bleeding. So you are bleeding steam from the turbine at intermediate stage. Okay, you can see this is one turbine, no reheating. So I take some steam from the turbine, and it may be at some pressure of P1. So at P, not P1, but at some P. I don't know what the value of the P is, at some P, pressure value. Okay. So then I put a heat exchanger here. And this one is that heat exchanger. Okay, then what I have is that from the condenser outlet, what I will divert that outlet to the open feed water heater here. So it goes that way. The open feed water heater, you can see this one comes there and that one comes there. And this one is that you have the mixing here. So this open feed water heater. So this open feed water heater, as the name says, that mixing is allowed. Okay. So you have to, there is mixing allowed inside this open feed water heater. So this one's at pressure P, and since this is heat exchanger, so you have that constant pressure. So the extracted steam from the turbine has a pressure P, but the condenser outlet has a different pressure. Okay. But what we should have is that we should have the same pressure here. But that P extracted steam, it has more pressure than the turbine condenser outlet. But we know that heat exchanger is isobaric. So by the heat exchanger here, I mean that open feed water heater. Therefore, add pump. So we should add the pump at the condenser outlet so that you have the same pressure for this fluid as well as for that fluid, so that you can have the mixing process here. So I erase that part here, and I am adding, erase this one too. So I will add a pump here. So pump 2, and then goes back to pump 2, and then from that pump 2 goes to open feed water heater. And you can see there is steam and there is that water here, that is two different fluids, but at the outlet you have one. And then I add one more pump. This is pump 2. And this one is pump 1 actually. Pump 1, and this one is pump 2. And what we do is that by using this pump 2, I increase the pressure from this steam pressure, extracted steam pressure, to the boiler pressure, because that this one should also has different pressure than the boiler. So P of the boiler is also greater than P steam extracted. Okay. Therefore, what we will do is that add pump. Okay, so this is the main working principle of the open feed water heater. And you have to notice that now I have one in mass flow rate, so that you have that m dot here, the m dot inlet. And this m dot is divided into two parts. And the one part is that y multiplied with m dot, and the other one is that 1 minus y multiplied with m dot here. And this y value is between 1 and 0. Okay. It's a fraction. If you have, for example, that 1 kilograms per second into the turbine, and half can go to the condenser, half can go to open feed water heater. Or it can be two, that it is one, it can be 70% here, 30% here. At the end, it is a fraction, and it determines how much of the steam is extracted or blended for this open feed water heater. Now let me put some numbers here and draw it on the TS diagram. So I will put a 1 here, and then you will have that 2. So actually, let me start from the beginning so that we are in accordance with the previous numbering. So it doesn't matter where you put the numbers, but so 1, 2, and then you have this so outlet here, which is at 3, and then you have the pump outlet 4, then you have that boiler, and then you have that 6 here, and then you have that 7 here. These are just numbers, and then you have to put these numbers on this chart here. And I will write the values that are given in the table here, so that 10 kilopascal, 15 megapascal, 600 degrees Celsius with 1.2 megapascal of open feed water heater. So you have that 10 kilopascal and 15 megapascal And also that you have that 1200 kilopascal for open feed water heater. Okay, and the peak temperature is of course 600 degrees Celsius. Now, if I work out with the pressure values, for example, so you can see that pressure at 1, which is condenser, is isobaric, which is same as pressure at 7. So P1 is same as P7. And the P2 pressure is same as P6, and it is same as P3. So P2 is same as P6 and P3. This one is A, and this one is B part. Because this is isobaric, you have the same pressure for inlets and outlets. Therefore, P2 is same as P3, and P3 is same as P6. Now comes the P4 value here. That P4, since it is boiler, should be same as P5. Okay. So 1, 2, 3, 4, 5, 6, 7. You can see the pressure values. We have 3 pressure lines. So that one is 10 kilopascal, one is 15 megapascal, and the other one is 1.2 megapascal. So let's draw it on the TS diagram here. So I will just start from the 1. And let me also write the values of this one, for example, P1 and the P7. So these are the minimum pressures because these are the inlet for the outlet for the turbine, and this one will be 10 kilopascal. And the P2, P3, and the P6, these are intermediate pressures, which is 1200 kilopascal. And the P4 and the P5, these are the maximum pressures because you are using the boiler here, and this is the second pump stage, and therefore here we will have that 15,000 kilopascal. Now let's show it on the TX diagram here. So we just start from the 1, where you have that 10 kilopascal, and it will increase the pressure to 2, which is 1.2 megapascal. So that 1 is here, 1. So it will increase to P3, and the P3 value is here. And see that it will be isentropic again. This is 0.2. Okay, 1 to 2, and then goes to 3 stage, and the 3 is also, so here this is the pump inlet. Okay, you can see this inlet, and therefore here you will have that inlet, and the X is 0. Here also inlet, and the X is 0. So that, so from 2 to 3, I don't know what happens here. I will find it later, but I know that from 3 to 4 is again pump. So that 3 is here, so X is 0, and you have that 4 here. 4 is here. Okay, you can see that 1 to 2, which goes from that. So let me write it here. 1 to 2, it happens from that 10 kilopascal to 1200 kilopascal. And then you have that 3 to 4, it goes from that 1200 kilopascal to 15,000 kilopascal. This is the second pump. Okay, for these cycles that I was having here, that is good. Start with pumps. Okay, because pumps are easiest ones. At the inlet of the pump, you should have 0 quality. It should be isentropic. It should go to another state in an isentropic manner. The pumps are the easiest ones to start for the TS diagram of these cycles. And then from that, 4 to 5, you have the boiler with a peak temperature of 600 degrees Celsius and with that pressure. So I will be here. So with the boiler part. Let me do that. This one's 0.6. And then from that 0.7. 5. Actually, this is boiler outlet. This is 0.5. This is 0.5. So from this 0.5, which is the turbine inlet, and that one drops to a value of 7. This is the condenser. You can see that it drops from 5 to 7, and this 7 is at 10 kilopascal. Okay, so I should go from 5 to 7. Okay, and this is the 0.7. So I have done that part, and now goes from the 7 to 1, and this is the condenser. Let's do that. This should get the isobaric line here. And the 7 to 1, it is condenser. So I will have that chart, and this one, and that one. Okay, now let's find the rest of the unknowns here. The rest of the unknowns is that, so I don't have the 6 here, I don't have the 2, and I don't have the 3 values here. So I have actually 3 and the 2 is there, 6 is not there, 1, 2, 3, 4, 5 and the 6. Okay, I should find it. So find points 5 and the 6. Okay, let me find it. So firstly, so 5 is also there. 1, 2, 3, 4, 5, 6 only. Only I should find the 6 value here. So 0.6. So I know that the 0.6 is extracted to open feed water heater here. This open feed water heater here has a pressure of 1200 kilopascals. So, and it is also isentropic. 5 to 6 is also isentropic. So 5 to 6, it is isentropic because it is turbine. And 5 to 7, it is also isentropic. Okay, and therefore 6 will be on the 1.2 megapascal line, which is this one. So I should have that 6 here. So let me erase this small one here and put a different arrow here. You will have that arrow. And the 6 will be on the 1.2 megapascal line, and it should be also isentropic. You can see that 5 to 6. And this is the 0.6. Okay, and this 0.6 is alone, but I should meet this 6 with the 2 and with the 3. Okay, and now what happens in this open feed water heater? So let me show it here so that for this open feed water heater here, one here, you have the 6, and you have this 2, and you have this 3. This one from turbine, and this one from condenser. So 6 has higher enthalpy than the 2 because it comes from the turbine, and the 3 has higher enthalpy than the 2. So that H6 more than H2. So you have that 6 comes from turbine. And the enthalpy of the 3 is more than enthalpy of the 2 because here you have that mixture process. So this one increases the energy of that one after mixing process. Okay, since it is the mixing process. So due to that mixing process, you will have that more energy for, due to mixing process, you will have that more energy at 3. And now what will happen is that the energy of the 6 should drop. So if I go back to here, the energy of this one should drop. So how it drops in that way. Okay. So energy of the 6 drops to 3, and the energy of the 2, where is that one? This one, increases to 3. So you can see it. I will go, this one is constant pressure because it is open feed water heater. Okay. This one is open feed water heater here. So this open feed water heater has the same constant pressure. Therefore, from that 3 to the 3, you have the isobaric line. From that 6 to 3, you have the isobaric line. You can see that all of them are isobaric lines. At the end, you are meeting at point 3. Okay. And this is the general configuration for the open feed water heater. So by adding open feed water heater here, let's see what is the advantage. The advantage is that you have increased the efficiency of amount of 1.3%. The quality has dropped. Okay. And since you are using 2 pumps, that you have more work, and also work of the turbine also has dropped, but at the end, the efficiency has increased. This is the open feed water heater in this turbine cycle. But the drawback of this open feed water heater is that you are extracting steam. Okay, if you extract more steam, it means that. Let me use different color here. So here what we are doing is that we are extracting steam. So extracting steam means that, so using power of turbine, instead of using, what it should be that, so instead of using, you are decreasing. So you are decreasing power of the turbine, because with that steam, the turbine would do some useful work and it give you the electricity. But what you are doing is that you are using that steam for only heating purposes. Therefore, so if you increase this one, so that power of turbine will drop. So how do we know that it will not drop or it will drop? So all of them are done by the simulations. So you have the computer simulations with different components. You are playing with the values and to get the optimum values for the cycle. Because as the number of the components increase, it is very difficult to solve the problem with pen and the paper. Okay. So therefore, that for the cycles that you have lots of components, you have to use the computer simulations and find the value of the efficiency for the cycle. Okay. Good. So I have done the modification number 6. You can see that at each modification you have the increase on pressure, but at each modification you can see in that direction that you are increasing complexity. And as the complexity increases, what it means that use some computer. Because otherwise you cannot work out these lots of, you can see that in the next one you have the reheating, you have the open feed water heater, closed feed water heater. Okay, so this process is much more difficult than the previous ones. Okay. Now let's see that process number 7. So now we have that closed feed water heater. So it was open. Open means that you take the steam, mix, and get outlet. But for the closed feed water heater, now let's see that. This is the turbine here. Okay. I take the steam from the turbine. This is the open feed water heater. And you have that condenser outlet. And this from, you will have that, so one outlet. So here you have that mixing is allowed. So what the opposite may happen, so that what you have is that you have the turbine, but here you will need some condenser pump. Here you will need some pump anyway. So you have that outlet with pump. So you have the turbine. You have the closed feed water heater. This one is closed. And for this closed feed water heater, again, I will use the condenser. I will use the condenser outlet with pump. I will use the turbine again, no problem, everything is okay. But here you don't have the mixing process. So since you don't have the mixing process, what happens is that it goes in that direction and it goes in that direction. Here you don't have any mixing. Okay, so this is the closed feed water heater, and each of them has advantages about it and disadvantages. Okay, you have the cost here, and you have that mixing here, okay. And you have the maintenance here. So these are, you know, that separate chapters, and therefore, so when you use this open feed water heater and the closed feed water heater, it depends on the type of the application. Now we will add this closed feed water heater to our cycle. Let's see what happens to our efficiency. Okay, this will be the next modification to Rankine cycle. Now let's do that. So what I have is that I have one open feed water heater, one closed feed water heater, and one reheater. So I have one open feed water heater, one closed feed water heater, and one you have the reheater. You can see the number of components, so it has increased, and it is now becomes difficult to analyze these processes in one pen and the pencil, as a pen and the pencil problem. So you have this boiler here, okay. And from that boiler you will have this turbine. Since you have the reheating process, you will have the turbine 1. Turbine 1, and that from that turbine 1, so let me see how much time do I have. So that from that turbine 1, you will have this boiler back to this boiler, okay, and then back to turbine 2. Okay, and then from this turbine 2, you will have that condenser. Let me add it here. Okay, now comes the feed water heaters. I will have the open feed water heater here, so again I will need the pump, because I don't know what the pressure of the feed water heater is, therefore I will need the pump. So here I need the pump 1. Okay. So why do I need it? So since don't know, so that actually not don't know, let's say that, so that pressure of open feed water heater, this one, is greater than pressure of condenser. So therefore we need pump here. So then you go to open feed water heater here. So there should be some extracted steam for that open feed water heater. So you are taking this one from this turbine 2. And then from this mixing, you have the outlet, which is one outlet. So you will have that here. Okay, now comes that next one, which is a closed feed water heater. So let me add it here. And we take the closed feed water heater. In the question says that, let me go back to the question. So it says that the closed feed water heater and the reheating, this one, these two, you can see that they are at the same pressure. Okay. So it means that what you're doing is that, but this one, so that P of closed feed water heater is same as P of reheater. Okay, so I can take the one line from this one. So I can take one line to closed feed water heater. You can see this is the similar process. Here, again, you have extracting steam. Here you also extract steam. But if you pay attention to directions, you will have one more direction there, you will have one more direction there. Okay, and you have also direction there, and you have also direction there. You have also direction 1. You can see that you have different directions. And from this open feed water heater and the closed feed water heater, so you don't need the pump here. In between, you don't need the pump. Okay, because that you are going in one line, and for that one line, you don't need the pump. Okay. But at the end, what you will have is that, so this one, so let me finish this process here. So the outlet, this one is the outlet for that one, and this outlet goes that way. Okay. And then, so you have one more component here. So why do you have another component? Because the outlet of open feed water heater and the closed feed water heater, they should mix. Okay, so this one goes that way. You can see. So at the end, you should mix them and send back to the boiler. And to mix it, you are using some mixing chamber. Okay. By using mixing chamber, I am mixing that one, the open feed water heater outlet, and the closed feed water outlet. Okay. Okay, but you should know that This mixing chamber is also heat exchanger. So this one is heat exchanger. Let me add it. So heat exchanger, and the P is constant. And from that one you go to boiler, and this is also heat exchanger, and you have that constant pressure. So constant pressure and the constant pressure. So it means that that pressure that leaves the open feed water heater should be the same as this. Boiler pressure, closed feed water heater should be the same as boiler pressure. So I should add a pump here. So I have another pump here and another pump here. Okay, so that this one will be that second pump, and this one will be that third pump. Okay. So why do we need it? So because that P boiler is more than P condenser, closed feed water heater, and this one is that since that P boiler is more than P open feed water heater. Okay. So if you do that, you will have that chart. You will have this way and that way. They are mixed here, and then you have the boiler. The next lecture, I will continue from this chart and write the numbers and plot it. So I'll stop the recording.